All right, so we ended up, I said we would save these last two types of probability um, for our beginning here. So last time we talked about finding area underneath the curve, our normal distribution curve, standard normal distribution curve. And we said the reason why we care about those is because they correspond to probabilities. And then we looked at how those can look. So we want to know the probability our variable is less than something, that's area to the left. If it's greater than something, that's area to the right. We could have between, or we could have the two tails. Okay, those are our four types of areas we found last time. Okay. And these last two are a little weird. Okay, so take tables we. Okay, you're welcome. And these last two are a little weird, so it's a good place for us to stop. I didn't want to rush through it at the end of last class. Okay. So E, that's another less than probability, so that part's not interesting. That we want area to the left. But if we go to our table and we try to look that up, we try to look up negative 4.01, what's the problem? It's not on there. Yeah, it's not on there. Okay. As far as our tables go, okay, to the left is negative 3.49. Okay. So on this one, we would just kind of have to use our brain instead of the table. Okay, so let's think about what's going on. Anybody need tables? Did I get everybody? Good. Let's think about what's going on. If we look at the furthermost left, a z-value on our table, it says the area to its left is 0.0002, so really tiny. Okay. And if you look at the trend, the further we go to the left, the smaller the area will be to the left of our z-value. So anybody got any guesses on what we're going to say about this one? Yeah, so it's going to be smaller than 0.0002. They're trending, right? The further we get to the left, the smaller our areas are getting. And it's actually going to be a lot smaller than 0.0002. So you got any thoughts on what we're going to say? On this one, we would say that our probability is approximately what? What number are we getting close to? 0. Yeah. So this one's something really, really tiny. So we would say we're approximately 0. Okay? We have a situation like that. Maybe I spelled that wrong. Okay. So technically, it's not actually 0, because remember our curve goes forever to the left. It goes all the way off toward negative infinity. So we've always got some tiny little number there. We don't actually get all the way to 0, but it's close enough. Okay. The real probability is probably like 0.00000001 or something like that. When they get that small, it's okay. We'll say it's basically 0. We're still in that one? F similar, but let's look at what's happening with it again. This is area to the left. But if we try to look in our table for 3.98, again, 3.98 is not on our table. The biggest z-value we have on our tables is positive 3.49. So this one's going to be even further to the right than what our tables give us. If we look at the biggest z-value on our table, it gives us an area of 0.9998. And as we go to the right, our areas are getting bigger and bigger. So we're gonna have something bigger than 0.9998. Anybody got any guesses now? Approximately 1, yeah, because remember on these, the smallest we could possibly have, even in theory, is 0. The biggest we could possibly have in theory is 1, because it's probability. Got to be between 0 and 1. So here, bigger than 0.9998, we're going to say it's approximately 1. Approximately 1. So if you run into that situation, that's what we'll do. That's not going to be like a common thing that we deal with all the time. But that's why our tables are not like way bigger. Because once you get out on the edges, the probabilities get really, really tiny. Questions on those? Okay. All right. Well, that's really it for 6.2. Okay, that's it for 6.2. Anybody else need tables? I think we had a couple. Okay, good deal. I try to catch you as you come in the door. Sometimes I miss some people. All right, so get this ready for our next section. Okay. If computer doesn't crash or something. Let's see what's going on. All right. Section 6.3. Oh, also, what do I do with it? You might want to put these 2 dates down. I think I've got our test 2 and test 3 scheduled. Okay. So I believe test 2 looking like it'll be on October 21st. Okay. And then test 3 looks like it'll be on November 16th. Okay. And I'm actually a little bit on the fence on that one. That's the week before Thanksgiving break. So I don't know what we'll do. We don't need any extra time to push it back, but I might make it where you can take it on the 16th or the 18th, up to you. Okay. Right now, I've got it scheduled for the 16th. Okay. That's it. The 16th will definitely be an option for testing. Okay. All right. So all we're doing in section 6.3 is we're taking our new skill of finding these probabilities out of our standard normal distribution tables and applying it to some problems. So the way all these are going to look is we're going to have some normal distribution given to us. Okay. And it's going to ask us about a probability involving that normal distribution. And the way we'll find the probability is we'll use our standard score formula, okay, to take the number and turn it into a standard score, a z-value, and then find the probability using the standard normal table. That's how these things are going to play out. Okay. So let's just look at our first one. We don't really have anything new to introduce. We're just putting some stuff together. Okay, so look at this one. And again, our textbook's a little wordy. Sorry about that. I actually deleted part of this. So I actually shortened it up a little bit. This one says, Dairy Delight Farms has been milking cows for many generations. They have calculated that on average, the milk production per dairy cow over a month's time is 1,931 pounds with a standard deviation of 67.1 pounds. The managers noticed that the milk production from their cows seems to have been slowly decreasing in the past couple years. So what we want to do is we want to determine the probability that a random cow chosen from the farm produces less than 1,831 pounds of milk per month. Assume that the milk production from the cows is normally distributed. So that last little piece where it tells us to assume that our data is normally distributed is important, and because that tells us that we're going to be able to use our standard normal distribution to find these probabilities. Okay. The other things we need to know, okay, this distribution it gives us, okay, with a mean of 1931, standard deviation of 67.1, it tells us that's a normal distribution, okay, but it's not the standard normal distribution. So what we're going to want to do is to transform this stuff, okay, into something we can work with our standard normal distribution, and then we can find those areas to give us the probability we're wanting for. Okay. So to do that, we need to pay attention to the mean and the standard deviation that we're given. Okay. So this one says on average, or the mean, cow produces 1,931 pounds of milk per month. That's our mean. And then our standard deviation, sigma, 67.1 pounds. And then this other number it gives us down here is part of the question, because it says determine the probability that a random cow produces less than 1,800 or 1,831 pounds of milk per month. Okay. So that's the one we want to know the probability for. Okay. And this part that we want to know less than that will be important in a second. Okay. So we want to work with standard normal distribution. We've got a mean and standard deviation and a number to change. So what we're going to do is we're going to use our Z formula. That formula, that's x minus mu divided by sigma. Take this 1831, that's our x. Change that into a Z, a number on our standard normal distribution. So to do that, let's see, does that show up okay? So the number we're wanting to change, 1,831 pounds. We're going to subtract the mean, which is 1,931 pounds, and divide by the standard deviation, 67.1 pounds. And we're going to see what Z value we get out of that. Okay. So remember on these we're rounding to 2 decimal places. I think I told you that would be obvious why, but I didn't mention why after I gave you the tables. The reason why we round to 2 places is that's all we have in our tables. So it's just not useful to leave any extra. So what do we get there? 1831 minus 1931, and then divide our answer by 67.1. I got negative 1.49. That's my Z. So what's going on here is we're going to take our probability question and transform it into an area under the curve problem. So right now we've got a Z value of negative 1.49, and to get a probability we need to come up with some type of area under the curve. Which type of area we want, left, right, in between, or two tails, depends on the question that was asked. Okay, so if we go back and look at the question, it says we want to determine the probability that a cow produces less than that number of pounds of milk. Okay. So what we're looking for probability, now that we've changed it to a Z, that Z is less than negative 1.49. What type of area is that going to be? Left, right, in between, or two tails? Yeah, remember how to tell last time it's less than, that points to the left. And so we want the area to the left. This tells us we want the area to the left. So we want the area to the left of negative 1.49 from our standard normal distribution. So how do we find the area to the left? What do we have to look up? Just look up the z, right? We just look up negative 1.49. Okay. Right, area to the left, we just look it up. Area to the right, we look up the opposite or do the complement rule. Area between, we look them both up and subtract the areas. Area in the two tails, we find both and add them together. Okay. Area to the left, we'll go to our normal tables, look up negative 1.49. Gives us 0.0681. Is the area to the left of that z value. So probability of a cow producing less than 1,831 pounds of milk per month, 0.0681. Or if you want to think about it, that's like a little bit less than a 7% chance. 6.81%. You change it to a percentage. Questions on any piece of that when I walk back through any of it we need to? Everybody's okay with it? Sure are quiet today. That's it. So we started off with the problem about cows. We changed it into a problem finding an area under our standard normal curve, and we used that area to answer our question about cows. We can do the same thing with anything, any kind of data that we know or are told has a normal distribution. Do that same thing. So no questions? That's kind of concerning. Okay, let's look at the next one then. We only have a handful of these. We don't have a lot of them to do today. It's got the stuff in there for the TI-83 or 84 graphic calculator if you want to look at it. I left it in. All right, let's look at a different problem here. It says, guests must be at least 40 inches tall to ride Splash Mountain at Disney World. If heights for 6-year-olds are normally distributed, that tells us we can use z. We can use our standard normal distribution. With a mean of 3 feet 9 inches and a standard deviation of 2 inches, what percentage of 6-year-olds are allowed to ride Splash Mountain? Okay. That's a good question. If you're making a theme park ride, you want to try to make sure most of your customers that want to ride the ride can ride the ride. Okay, so what do we know? The main important part. Okay, it tells us heights of 6-year-olds are normally distributed. That tells us we can use our standard normal distribution. So what else do we need to know? It tells us the mean. It says the mean is 3 feet 9 inches. Standard deviation is 2 inches. And then what do we want to change to z? Well, it tells us, it asks us what percentage of 6-year-olds are allowed to ride Splash Mountain. We'll go back to the beginning. It says they've got to be at least 40 inches to ride Splash Mountain. So 40 is our number that we want to turn into a z. 40 is our x, 40 inches. That's our x. So we've got a little side calculation we need to do on this one, or that it's probably easier if we do anyway. This 3 feet 9 inches, since that's mixed units, and everything else is in inches, it's probably easiest if we change this instead of 3 feet 9 inches, if we change it to all inches. So how many inches are in a foot. 12, yeah, so 12 times 3 is 36, plus 9 would give us our mean in inches is 45 inches. Just makes our other calculation a little more clear. So then, get our z. We want to figure out what 40 inches is on the standard normal distribution. So we take it minus our mean, we figured out was 45 inches. We're going to divide that by the standard deviation of 2 inches. Round to 2 decimal places and see what we get here. So 40 minus 45, and then divide that answer by 2. My calculator gives me negative 2.5, but since we're doing 2 decimal places, I'm going to write the 0 down, negative 2.50. Okay. So what's going on here is that we now have a z value on the standard normal distribution curve. We got negative 2.50. And to figure out this probability, we want some type of area under the curve. So we need to think about which type we want. Do we want left, right, in between, or two tails? So we look back at our problem. So we want to figure out what percentage of 6-year-olds are allowed to ride Splash Mountain. And they're allowed to ride Splash Mountain if they're at least 40 inches. So what's at least mean? Yeah, equal to or greater than. So greater than or equal to. And greater than or equal to. So what we want to find our probability, we want the probability that our z value is greater than or equal to negative 2.50. So which direction is that going to be? It's going to be to the right. We want to the right because it points to the right. And so we want this area. Okay. So we want the area to the right of negative 2.50. How do we get that out of our tables? Yeah, we can look up the opposite. Right? We can look up the opposite because remember our tables give us area to the left. So one way we can find area to the right of a z is to look up the opposite. So here, instead of looking up negative 2.50, we can look up positive 2.50. Okay. We look up positive 2.50, get an area of 0.9938. Okay. And that's going to be our probability on this one. So what percentage of 6-year-olds can ride Splash Mountain? Well, change it to a percentage more than 99%, okay, 99.38%, what we're expecting. Questions on any part of that one? Yes, ma'am. No, it's fine as a decimal. Yeah. It's just easier to think about, like when you're actually thinking about what it's asking, it's easier to think about it as a percentage. No, decimal's fine. Any questions on that one? These problems are all really similar to each other. So on each problem, you'll have a different mean and standard deviation. And then you'll take whatever number it's asking you about, change it to a z. And then you have to figure out which type of area you want. Do you want the area to the left of that, to the right of that, in between, or two tails? That's it. Okay. So once you get the hang of it, they're not bad. Okay. No other questions on that one? Good to go? Okay. Huh? Okay, let's look at this one. It tells us, as adults, our body temperatures are normally distributed with a mean of 98.6 degrees Fahrenheit and a standard deviation of 0.73 degrees Fahrenheit. That information is actually getting a little bit out of date because there have been some studies here lately that said the average healthy body temperature is actually going down. So, anyway, that's the standardly accepted thing right now. Then it says, sometimes our bodies increase temperature and we say we have a fever. Other times our body temperatures might drop to a place of hypothermia. It says extreme fluctuations in either direction might be signals we need to seek medical help. With this in mind, answer the following questions. Okay, so we've got a three-parter coming up. But keep in mind 98.6 is a mean for normal body temperature. Right? Your personal normal body temperature might be more or less than this. Okay? So if you don't know that, that might be a good kind of thing to check sometime when you're not sick. Okay? Check what your body temperature is so you know if it how it fluctuates. I say that because, like, if your normal body temperature is like 97.9, right, or something a little smaller than this, then a 99-degree fever, okay, is a bigger deal for you than it is for somebody whose normal body temperature is 98.6. Right? That's not really a fever for somebody like that. Off topic, sorry. Okay. Let's look at part A here. Okay. This one says, what percentage of healthy adults have a body temperature which is between 98 and 99 degrees? Okay. So on all these, we're going to be working with the same normal distribution. Here our mean is 98.6. Our standard deviation is 0.73 degrees. Okay. So we want to know what percentage of healthy adults have a body temperature between 98 and 99 degrees. What temperature do we need to change to an X on, to a Z on this one? Both of them, right? We've got two. Because we want to know something about both of these. We want to know the probability of it being between these two. Okay. So we'll have to use our Z formula twice. Okay. So let's see, I'm going to say Z1. I'll do 98 minus our mean, which is 98.6, divided by our standard deviation of 0.73. Those two numbers on the last slide. See what that one gives us. 98 minus 98.6, and then divide by 0.73. On that one, I get negative 0.82 when we round. Okay. For the other one, we use 99, so 99 minus 98.6 divided by 0.73. See what we get there. For that one, I get a Z of 0.55 when we round. Okay. So the picture of what's going on here, okay, I've got two Z's on the standard normal distribution. Okay, what were they? Negative 0.82 and positive 0.55. They're somewhere in there. And then what area do we want on this one? Between. Between's pretty easy. Okay, there's not a lot of ways you can word between. So it says we want to know the percentage of healthy adults that have a body temperature between 98 and 99. We want the area between these two z values. All right. So then what do we do? We want the area between, how do we find that? Yeah, we'll look them both up in the table and get the areas to the left of both of them and then subtract, okay? So let's see, if we go to the table, if we look up 0.55, again, I get 0.7088. And if I look up negative 0.82, I get 0.2061. When we subtract, which one will we put first? The bigger one, which is 0.7088. Yeah, so 0.7088 minus 0.2061. Do that subtraction, we'll get our probability here. So 0.5027. So as a percentage, it's about 50%, a little bit more, about 50%. Okay. So the question asked, what percentage of healthy adults have a body temperature which is between 98 and 99? About 50%. So that means about 50% are not between 98 and 99 also. Questions on that one? Are you bored with these? I only got like 2 more. Look at part B. Part B says what percentage of healthy adults typically have either a consistently high body temperature of more than 100 degrees or consistently low temperature of less than 97 degrees. So this one's more interesting. If you remember, we're not talking about people with fevers and things like that. We're just talking about normal healthy body temperature. So what's going on? We got 2 temperatures to change to Z again. All right, because we want to know one is more than 100, the other one's less than 97. Okay, so it doesn't matter which one you call 1 and which one you call 2, but call that one X1, this one X2. So I'm going to work with 100 first. So 100 minus the mean of 98.6 divided by 0.73. Again, those numbers are from the first slide again. Okay. So what do we get? For this one, I get a Z of 1.92 when we round. For the second one, 97. And 97 minus 98.6, and then divide by 0.73. That one I get negative 2.19. Okay. So then if we make a little sketch, and you can probably pick it up from the wording here, but Sometimes a little sketch helps. What's going on? We've got our curve. We've got two z's on there. We've got 1.92. We've got negative 2.19. And what do we want? On this one, we might have to read a little more carefully. We want body temperature more than 100 degrees. So that was this one. So we want more than 1.92. So which type of area is that going to be? Left, right, in between? That one's going to be to the right of 1.92. We want this area. And we also want less than 97, so less than negative 2.19. That's going to be to the left of this one. So this is a two tails problem. Two tails problem. So we find both the areas and then we add them up, or add them together. Here, I'm going to look up negative 2.19 first. Negative 2.19, get 0.0143. And then I need the area to the right of 1.92, so what do I look up? Well, area to the right of this one. I'm going to look up the opposite. Look up negative 1.92. Negative 1.92. 0.0274. Let me add these together. Order doesn't matter here. See what we get. We got 0.0417. Questions on that one? All right, something to think about, especially if you're going into nursing. Okay, sorry for everybody else if you're bored with it, but so on the right side, we're talking about people whose normal healthy body temperature is more than 100 degrees. That seems real weird, right? It is pretty weird, but looking at this, we've got like almost 3% of people. So I feel kind of bad for them right now when if you're having to go somewhere and get your forehead scanned before they let you in. If you go and your normal healthy body temperature is 100 degrees and you go and they scan you and it's 100, they turn you around and tell you to go home, even though nothing's wrong with you. Something to think about. Usually 100 degrees would mean you have a fever, not always. Questions on that one? Okay, one more. This one's just worded a little differently. It says, what is the probability of a healthy adult having a body temperature that differs from the population mean by more than 1 degree? So on this one, we gotta remember our population means 98.6. So if it differs by more than 1 degree, what does that mean? Well, so it could be more than 1 degree below the mean. All right, so there we would want the ones that are less than 97.6, or we could be more than 1 degree above the mean. So for those, we would want everybody that was greater than 99.6. That makes sense how I got that one. 1 degree below is 97.6, so to be more than 1 degree away, we would have to be less than that number. Or on the upper side, if we add 1, we get 99.6, so we want the people that are more than that. Good on that part? If you get that part, then the rest of it's just like the other ones we've done. So here I'm going to call it Z1 or X1. It's going to be X2. So we plug it, run it through our formula. 97.6 minus 98.6 over 0.73. Gives me a Z of negative 1.37. This one, they get 1.369, so it rounds up to 1.37. And then Z2. What we're going to get on this one? Yeah, we're going to get positive 1.37. Why does that happen? Why are they just opposites? Because on this one, we're going 1 degree down from the mean. This one, we're going 1 degree up from the mean. So 1 degree down, that many standard deviations down. 1 degree up, this many standard deviations up. It makes sense. They come out opposites. So then for our picture, here's our curve. We want the ones that are more than 1 degree above average, or the ones that are less than 1 degree below average. So again, we want the two tails. And on this one, if you remember the shortcut, our Z values are symmetric, they're opposite, so what's our shortcut? We can just look up that one tail and then do what? Yeah, you look them both up, Adam. But if we just look up negative 1.37, what do we get? That's 0.0853. And I don't even have to look at the other one because they're symmetric, so I know they have to be the same. So I can just do 2 times 0.0853. We'll get our probability there. That's a little, not much of a shortcut, but it's a little bit of one. Our probability of 0.1706. Question on that one? So all the problems in that section are going to be similar, right? You'll have some normal distribution where it gives you the mean and standard deviation, and then ask you about some probability of some data value in that distribution. So you change it to a Z, and then find the probability by relating it to some area underneath the standard normal distribution curve. Left, right, in between, or two tails, depending on how it's worded. All of those. No questions? I don't know. Everybody sleepy today? I'm sleepy too. Okay, All right, so that's the end of that. Let me